And I wrote a tool, and I like to share it. It won't take long. It's something I've been working on and off for some time. So yeah, let's dive into it. It's called, KadNode. Okay, I'm not very creative in this way, but okay. I need to, yeah. Okay. Yeah, it's yet another peer-to-peer DNS-like system that has some special properties, and it's meant to be simple because, yeah, I'm one person and I don't have that much time for one thing. And its task is to just, well, what most people understand to be DNS is to find IP addresses based on some identifier, which might be google.com, but I have a little bit of a different spin. And one important aspect was that it is decentralized and has a low footprint. So it can run on OpenWRT. There's also already a package, but yeah, it's not quite finished yet. So it will run on your homebrew OpenWRT router. And yeah, one main aspect in the way that it's different from classical DNS, it's that it uses a pet name system. So it's not really traditional DNS. You have links that look like, yeah, you have an example. It's basically some random, it's a public key in a hexadecimal format. And what basically happens is, yeah, you can use it for SSH in your browser or whatever, and you will get to the destination. And yeah, my use case, the motivation behind this is that I wanted something for a Freifunk community where we have some servers on the internet, and we use DNS entries like VPN1, 2, and stuff like that to access the servers. And I would like to have it a bit more decentralized and not relying on the DNS infrastructure. So to make Freifunk a bit more decentralized in that way, it can be also used inside the Freifunk network to have a decentralized DNS system. Yeah, and yeah, I thought it was a nice spin, a nice idea, and I wrote it, and it seems to work. Okay, how it works. Basically, it's a daemon running on the router or on your system and intercepts some special top-level domain that is not officially used. You can configure it, but by default, I have just used .peer-to-peer and yeah, and some different mechanisms to intercept it on different systems. There are packages for not only OpenWRT, but also Windows and Debian. And for OpenWRT, it has a DNS server interface, and you can tell the default DNS server on OpenWRT, okay, everything that ends with a top-level domain, P2P, is going to be resolved by this local service, which is basically a DNS server thing. Okay, and yeah, how is it? In what way is it decentralized? It is decentralized that it uses a distributed hash table, which I have just taken from the transmission bitrun client. So basically what it does, you take a 20-byte hash and it maps it to IP addresses. But I don't use it for files, to finding parts of files, but to find, yeah, for a public key, a bunch of IP addresses, which I then need to authenticate. Okay. Yeah, so what basically happens, I have a public key, I use the DHT, the bitrun network, to resolve it to a few IP addresses, and the other KadNode instance somewhere has a private key and can answer challenges. So basically the authentication works in that way. I send a random string, and what comes back is a signed string. And with a public key, I can say, oh, I can decrypt it, and if it's a string I've sent out, the random string, then I know, okay, the other side has the secret key, so that's the IP address I will forward to my SSH client I've just started, or yeah, whatever address I've tried to resolve. Okay, yeah. Challenges, yeah, it's so far not very fast. It can take up to 8 seconds to resolve a new entry, but 1 second is possible, but it needs a modified DHT. I'm working on that, but it will take some time. So, and what I'm also currently working on is to support TLS, because on OpenWT you have an HTTP server, and it uses a TLS implementation, embedded TLS library. And I thought, okay, I've also have a crypto library, why don't I use it? And it also uses a public key infrastructure, or my own, and I also can try to integrate it. So you can announce on the DHT network for BitTorrent, like the hash value of google.com with the real IP address of Google, and other instances can use the certificate authority certificates that you have installed in your browser, on your system, somewhere to verify that IP address. So actually you could resolve google.com using the DHT and get the real Google server. And that's something interesting. But yeah, of course we can use this to make our own certificate authority, use this yeah, X509 something certificates to have a decentralized DNS system. Yeah, and that's something funny, and I'm working on it to make it work, and so far it looks good. And yeah, some features. It's of course does IPv6. It's written in C, open source, of course. Some packages, local peer discovery. Okay, it's not important, but basically, yeah. Thanks. There's the code. I'm working on it, and yeah, if somebody is interested, have fun, and yeah, I will release it, of course, to make official packages when it's working. Thanks.
Done.
Questions? Oh yeah, we forgot questions. Anybody have questions?
Anybody? Really? Nobody?
So what's the approximate current footprint of nodes that host your service?
You mean what the footprint is, memory-wise?
Oh no, how many nodes already run your service? Or did you just start this and it's running on?
Oh, I mean, I already use, for example, the Debian BitTorrent tracker to bootstrap into the DHT network. Also, if in the local network, if somebody runs a BitTorrent client, which might happen, might not, then they will detect each other, and my program, KadNode will pretend to be a BitTorrent client, and will use it to bootstrap into the system.
Okay, so you're free riding on BitTorrent?
Basically, yes, but more, to be exact, I'm free riding on the DHT network, but since I use the vanilla DHT implementation that is used for the transmission BitTorrent client, it is, yeah,
so you're giving something
it's
back,
part of
right?
the network.
Okay.
So I'm not taking someone's resources or something like
okay.
that.
Cool, thanks.
I'm just curious, what was your motivation to use DHT? Because the typical DHT has the advantage that it scales very well for trillions or billions of data points, and to reach them it does a random walk with logarithmic lengths over the nodes, and random walks in mesh networks can be tricky because if I want to have the DNS of my neighbor and have to do a random walk of a few steps over my whole network, this might take a while. I think that's where your delay is coming from, partly.
Okay, fair point. A DHT isn't optimal for mesh network because the structure of the DHT net assumption doesn't match one-to-one to the how the links between routers are exactly laid out. In that case, yeah, it works, and I am going to modify the DHT a bit to make the metric that way, for example, to take into account the latency, so it will be a bit more efficient to work on mesh networks, but also the main motivation is for now to have it run on the internet. So, and there the DHT is a very good fit, I think.
Just another comment. I have a coworker who has written, I think, his dissertation on exactly this thing, DHTs in mesh environments, and he tried to modify the metrics to involve link costs, and he got nearly no positive effect at all. So I would do quite a bit of measuring before you start modifying DHT. The DHT has, at least if we are talking about KadNode has some very nice features which make it very easy to analyze and very scalable, and it's very easy to wreck these features by modifying stuff of it. So do a few measurements before you deploy the modified one.
Yes, thank you. Thank you for the warning. I've read a few papers and got some ideas, of course, but I don't plan on modifying it on a very basic level, more like a bit tweaking. I don't plan any big advances in that case because, yeah, no time. Thanks.
Any further questions?
No, it doesn't look like it.
Doesn't look so. So thank you very much for your new feature, idea, script, whatever.
Yeah, it's written in C, so it's a native program.
It's even a program. Yay!
It's a program, it runs, it doesn't crash.
Thank you very much.
Okay, thank you.
And I just got the information that we have another lightning talk. Just arrived seconds ago. So don't leave the room here. What is it about? I'm trying to figure it out. Okay, the topic is not decided yet. Because we need to switch it over there. There's an HDMI switcher.
That would be great. If you have one, that would be great.
Yeah, but native HDMI output is better than anything adapter. Okay, next talk, lightning talk, is held by Krishna, currently at the University of Dresden, and does want to tell us something about opportunistic routing. Give him a warm round of applause.
Good. Sorry for holding you all back before your dinner. I know this is a little bit too late, but I promise I'll be fast, and in 15 minutes we're all gonna go eating, right? First of all, let me introduce myself. I'm Krishna. A lot of you have seen me already in the last couple of days, but I work along with Simon in most of my work. Yeah. And we're from TU Dresden, right? So we are PhD students there. And what I want to talk about today is something called opportunistic routing. It sounds really cryptic when you first hear it, which it is also. What does it have to do with us, and why are we talking about this in mesh networks? This is what this short 10-minute lightning talk is going to be about, right? Good. So, what is opportunistic routing? In order to answer this, we have to say first that one thing we've been doing, say, wrong in the last, or a misguided approach of looking at networks, especially when we talk about wireless networks or mesh networks, is that we always abstracted these wireless networks as wired networks. This abstraction was very good for a multiple of reasons, which I'm sure a lot of you would defend. However, by doing such an abstraction, we lost something. We lost a very intrinsic property of the wireless medium, which is that everything that you send over a wireless network is a broadcast. Unlike an Ethernet cable, where if you send it out a cable, only the node that is, okay, it's back again. Only the node that's connected to you can listen to this, right? And opportunistic routing is a way of routing your packets in a way that you exploit this broadcast nature of the wireless medium. And what does it mean in real networks is that the one on the left that we see is how a mesh network or any network works today, right? If you have a packet to send from a source to destination per se, you will find what is your ideal route through which you want to route your packets, and you route your packets through this route. So there is this one hop through one hop through one hop that you say, this is my ideal route, shortest path, whatsoever, and you route it in this direction. However, what you could potentially do is use multiple of these paths, because a packet that is sent from one of these nodes is overheard by more than one node, right? Technically, both of them could help in forwarding this packet forward. This is by principle what is opportunistic routing, right? I'm sure you're already spurring out with questions saying this is completely maniac, then how do we take control over this? And this is what we are trying to tackle, right? These are the challenges that we try to tackle. But before I show you how we do that, I want to show you why we do that. Why do we want to use multiple paths, right? Which is pretty much right? At some point when one node, let's say, goes down or it moves, which is in a mobile wireless mesh, a node would just move around and your links change. And the time that you take to react to the link is the time that your routing protocol needs to really understand how the network is, and it has to reestablish the link. And if you have multiple of these links, then you already, if one of the node moves, you already have another link which works, which means your downtime is virtually zero, provided, of course, you have multiple routes and so on. And another thing is that you can achieve what in information theory we call the Shannon capacity, right? Or you can achieve the maximum possible throughput that you can achieve in a network, because the amount of data that you can transfer from one place to the other is limited by all the possible ways that you can go through. Therefore, by sending in multiple paths, you're basically increasing the data rate or increasing the throughput that each of your devices get, right? So this is the fundamental thing about, let's say, opportunistic routing. I'm here only to tease you about a lot of things, and if you have any deep questions, I would really love to explain you offline, because I don't want to overshoot my time here, right? Good. And here's just reiterating what I just said. And if you have a single transmission to make, your opportunistic routing protocol, whatever it may be, which is something that we are trying to work on, it has to determine a couple of things, right? First, not every node that is around you has to forward the packets. You have to have a smart way of saying how you route the packets or who should really forward the packets. And then again comes the question, how many packets should they really forward? Do they all repeat the same packets that I sent? No, that's quite wrong, right? And so these are the kind of questions that such a routing protocol will have to answer, unlike a traditional routing protocol, which does not care about the packets in itself. It just cares about the routes, right? So this is fundamentally that is different. And in order to achieve this, we need a smart way of coding packets, as we call it. It's called network coding, right? Network coding is what we use, let's to say, mix packets together. Because you do not just send one, if you want to send 100 packets from all the way over here to here, you do not send 100 packets in each of the link, obviously, right? Because that is definitely crazy. And imagine you sending 50 packets here and 50 packets here, and finding a protocol which knows what is the ideal way in which you route packets through one way or the other. And this is a function of an opportunistic routing protocol in a wireless mesh, right? And let's skip over this. So I have a couple of slides about how network coding actually works and how does it really help in us in order to make such routing protocols. However, I'm not going to go through this now because I would like to stick in this 5-minute lightning talk time. But if you would like, I would totally love to explain this to you offline, right? And it's quite exciting and interesting, I know. And just a summary about what we've saw. It's just resilient, first of all, in chaotic environments to do opportunistic routing. And you need nearly no feedback. You need very rare feedbacks, not per packet feedback as how Wi-Fi works today. You need a feedback for every 32 packets that you send, which means your amount of feedback that you send is cut by 32, for example, or 64, depends on. You trade it off with the latency of your packets, right? And there is no in-order arrival or such thing. So the packets that are flowing through the network can be in any order. So one packet can arrive earlier than the other, but network coding will fix it and deliver in the right order and something like this. And essentially, there's two advantages of using such opportunistic routing. One is you use all the paths available and therefore make it more resilient and more throughput. And you also make the losses in the network much better. So today's routing protocol, or today Wi-Fi in general, fixes losses by repeating the same packet one more time, right? And what we do with network coding is we code and send a packet again to make sure that we do not have to repeat the same packet. So imagine if you have 32 packets sent, I just send one more packet. This coded packet can fix any of the 32 packets that I earlier sent. It could fix it, which means if you lost one of those previous packets, this one magic packet, which is of the same size, will fix this loss. Good. That said, you'll all be coming up with this question, hey, dude, this sounds like unicorns to me. And I don't think this is practical at all, right? That's a very good thought. It's not very far from reality. And this is a question that also came to us, right? As a researcher, as a PhD student, which I am, I would like to answer this question myself. Which brings me to my second lightning talk of today. Surprise, surprise. Which is something called Rate Checker. We just published this online also along with Simon. Earlier today, we made this tool called Rate Checker. We made it earlier, but we just published it today. And this is a tool that we want to use to understand, first of all, how these links in the network are, to understand a network completely, not just saying what is, not just putting one metric on each link like any other routing protocol will do, but this metric for each rate in which there is. Because going back here, yes, so this particular link here is not just, you cannot categorize this as, hey, this is this % lossy, because in each data rate, it is a certain % lossy, right? An example routing decision could be if he has a little bit worse link to this node here, he could send in a worse link or a better link or a better modulation rate so that 2 or more people can overhear, and therefore it probably assists the transmission better. If the last part sounded cryptic, do not worry, that's okay. Anyways, the point is that we made a tool which is which we called it rate checker, which you can run on any of your routers in your community mesh network, which we would love for you to do that. And what it does, it analyzes your entire network in each rate, right? And it keeps a log of it. It says, hey, I sent so many packets in these many data rates, and I received so many packets in these many data rates, so you know not only the losses of each data rate, but also how the pattern in the losses look. If it's just a really random loss, control algorithms to do or to right. And for us, we make another program, or which we would also probably soon publish, which you can run again on this output that was generated by this rate checker tool to say how much advantageous would be an opportunistic routing protocol in your network. You could see that if there's 10 nodes and one node to the other node, if the data rate is 10 megabits per second today, if you just do an iPerf, and what would be the data rate if you used an opportunistic protocol potentially? Something like, I don't know, 20 megabits per second or 18 megabits per second. And this sort of data is really useful for me personally, for many of the people who would like to research more on what is the existing network because currently we have a lot of assumptions on how losses are, but for once we want to have a knowledge on how this really is in a real network, and of course publish all these results that we generate online, not just our observations on the results, but just the traces itself. So if anybody can run their own study. One of you is probably an enthusiast about this and want to make a rate control protocol better, and this is something that you could run in yourself to study more or develop a better protocol, right? So that's basically it, and of course it's GPL license. Thank you very much, and I'm open for questions.
Hi.
Yes.
So your first lightning talk sounds pretty fantastic. Maybe you can help me to better understand. So
yes.
To me, this sounds like what you're trying to do is what MIMO does on the physical layer with, spatial multiplexing is what you're trying to do, let's say, on layer 2 or layer 3. So, more on the digital side. And by, distributing the data that has to be transferred from source to destination, distributed with recoding and whatever, and those use all possible routes kind of at once in a very intelligent way.
That's a nice analogy, but it's very good how you mapped it there. But I think it's not quite accurate because we're not really multiplexing data here. It's the same data that is sent, but this data contains multiple parts of the information of the same flow. So it's in a typical MIMO, you would have different data for different users, right? It's the opposite here. You have the same data which goes through multiple nodes, and it converges again towards the destination.
Okay, yeah. Maybe I can ask you later about it. Yeah.
Cool. Yes.
I think I remember the BattleMesh in Aalborg where we had a long talk about network coding.
Yes.
So I assume this is from the same linear network coding package, the encoding, because it looks familiar.
Yes, the network coding part, or it is random linear network coding. However, this has nada to do with what you may have heard in Aalborg, because in Aalborg, I think it was given by Martin Hundebol, the guy who made this, and the network coding that they used was called interflow network coding, where they combined packets from multiple of these sources. Imagine there's different traffic flows in different regions, and you mix them together.
Sorry. In Aalborg, we had exactly this, that we have a single node starts transmitting data, recoding on the fly on every node to get around the retransmission. So we are not talking about this interflow stuff, which has been there in the research. We were talking about exactly.
It could be just a single node going, but I think the recoding was done with the acts that were going from the other direction to the other, isn't it?
It was just every node overhearing data.
Okay, then I'm mistaken. Then it's probably if this is true, then this is in the same direction. Yes.
So You have do you have a running implementation of this?
We are currently testing it. We're
On which hardware is this working? Because it's not quite easy to send variable rate multicast or broadcast in the term of Wi-Fi out. Some Wi-Fi drivers support this, some Wi-Fi drivers don't. Typically, broadcast is always base data rate or fixed data rate, if you're lucky. And it's not that easy to get multi-data rate traffic
You're
out.
right, you're right. So we use the ones with ATH9K, which support this. So this is the chipsets that we are using right now.
Yeah.
But not every chipset allows this. You're absolutely right.
A last question would be, what is the cost in terms of delay? Because I remember talking with the network coding people in Aalborg, and if you re-encode stuff, I think Batman Advanced had a partial implementation of this for testing. Then you have to wait sometimes to get enough data to decode your packet.
Correct.
And you have a window of opportunity, and you have to wait for the window, which means in some cases you must wait, which increase the delay.
Again, I think the one that's implemented in Batman is also interflow network coding. Simon, could you correct that? Is that right? What we have in Batman?
So the implementation in Batman is called Catwoman, and that's interflow. But I think in Aalborg there was also a discussion about play and cool, and that's intraflow, which is similar to what you introduced.
So, yes. Questions? Is that all? Or? Okay. Other questions?
Yeah? Somebody? Really? Nobody?
Yeah,
Okay.
me too. Really?
So,
Nobody?
thank you very much, Krishna, for your talk.
Thank you.
So in just a couple of minutes, round about 5, we will have the last talk for today. So don't stroll that far away. Stay here for the last talk about Altea. I don't know what it is. We will find it out.